We are group 5, and the topic of our paper is rethinking the inception architecture for computer vision. And below is not our names, it's names of the author of the papers. The first author of the paper is Christian, who is also the author of the Inception V1, the inventor of the Inception module, and the Google Net, the module the last team just presented. Okay. So in this paper, they first introduced the background of the inception structure and proposed several design strategies as principles for all the deep learning network designs. Then introduced the new structures and strategies as new modules or blocks in neural network, and show the world network structure and training procedure and evaluation and the low resolution result, and finally the result and conclusions. Okay, and here is the introduction. According to the title of the paper, the authors are going to rethink the architecture of the inception structure from different point of views. The background of inception is a module which is focused on not only the depth but also the width of the network. The model this paper proposed is named Inception V3, while the first version deep learning model with the inception module is Google Net, which is called Inception V1. And V2, V3 are proposed here, and the successors are V4 and the Inception ResNet. And very deep convolutional neural network model become mainstream since 2014. That's the year the Inception V1 got champion of the ImageNet. ImageNet is an image classification competition. And then it becomes a trend to increase the width and depth of the network structure. The Inception competitor VGG network from Oxford is an example for improving its accuracy, mainly on its depth of the model, and it seriously higher the requirement of computational cost and made the model size become fatter and fatter. The main purpose of the paper is to improve the structure of the inception. Compared to Google Net, evaluate the actual effect of the auxiliary classifier and just leave one of it. And they propose 4 new inception structure in the network as one of the greatest innovation in this paper is to improve the inception structures. The new structures are focused on its width balance, and they make its width of the network more controllable, and furthermore applying some tricks to handle the computational cost at the same time. And in the paper, the author proposed 4 design rules for all deep learning network, and call them design principles. And for the first point, that is we shouldn't decrease the dimension. The information of the feedforward network should not shrink too quickly. We should gently decrease the dimension of the network. And for the second point, we should ensure the dimension. The number of channels would make the network easier to recognize different features. And for the third point, the spatial aggregation is better solution. That is, they claim that using the one-by-one convolution or bottleneck layer is a great solution to care both information loss and performance. And for the final point, balance the width and depth of the network is the most important point. It claims that we would lead to better performance along with the principle 1, 2, 3. And I think this is the point the author thinks they are trying to make this model achieve.
Okay, just as the previous group has mentioned, using a one-by-one convolution followed by a three-by-three convolution aggregates the information from each channel and decreases the dimensions. Dimension reduction provides lots of gains in GoogleNet, not only preventing overfitting, but also helping the architecture to get rid of its heavy computation. Any reduction in the number of parameters results in a reduction in computational cost. With suitable factorization, we can end up with faster training. Besides, we can extend a bigger filter bank size while maintaining our ability to train the model. So, is there any other method of factorizing convolutions to increase the computational efficiency of the solution? And the answer is yes, and that is the essence of this paper. There are 2 methods proposed in this paper. The first one is factorization into smaller convolutions. For example, if there is a 5x5 convolution over the grid, there are 25 parameters that need to train. But if we replace it with a multi-layer network, such as two 3x3 convolutions, there are only 18 parameters that need to train, which help us to end up with a 28% computation reduction. However, this setup raises a general question. Does it suggest keeping linear activations in the first layer, or should we use rectified linear units, which is also known as ReLU, instead of linear activations? The results based on their several control experiments is that using activations was always inferior to using ReLU in all stages of factorization. Or you can just say using ReLU is always the better choice. This difference can be attributed to the enhanced space of variation that the network can learn, especially if we apply batch normalization to the output activations. And you probably are thinking about what if we apply this method again to these two 3x3 convolutions by replacing each of them with two 2x2 convolutions. And that's a good idea, but the editors provides a better solution, and that is the second method proposed in this paper, spatial factorization into asymmetric convolutions. By way of illustration, factorizing a 3x3 convolution into two smaller convolutions, or in this case, two 2x2 convolutions, cost us 8 parameters. However, using asymmetric convolutions, for example, a 3x1 followed by a 1x3 convolution, cost us only 6 parameters, but provides a similar receptive field as in a 3x3 convolution. In summary, factorizing a 3x3 convolution into two 2x2 convolutions represents only a 1/9 computation saving, and factorizing a 3x3 convolution into a 3x1 followed by a 1x3 convolution represents a 1/3 computation saving. So in general, factorizing any n by n convolution by n 1 by n followed by an n by 1 convolution costs us only 2 divided by n computation than usual. As n relatively large, a significant cost saving may lead to much information drop such that this factorization does not perform well. The editors suggest employing this factorization on median grid size, and that is n ranges between 12 and 20. And on that level, very good results can be achieved by using 1/7 followed by 7/1 convolutions.
Okay, the next part is about the utility of auxiliary classifiers. GoogleNet has introduced the notion of auxiliary classifiers. The original motivation was to push gradients to lower layers to make them useful, and improve the convergence during training by combating the vanished gradient problem in very deep networks. Also, Lee et al. Argues that auxiliary classifiers promote more stable learning and better convergence. Interestingly, authors found that auxiliary classifiers did not improve converge early in a training. The training progression of network with and without sidehead looks identical, and both models reach high accuracy. Near the end of the training, the network with the auxiliary branch starts to overtake the accuracy of the network without auxiliary branch and have higher performance. Note that GoogleNet used two sideheads at different stages in the network. The removal of the lower auxiliary branch did not have any effect on the final quality of network. This means that the hypothesis of GoogleNet that auxiliary classifiers help involving the low-level features is wrong. Instead, it may act as regularizer. This is supported by the fact that the main classifier of the network performs better if the side branch is batch normalized or has a dropout layer. This also gives a weak supporting evidence for the conjecture that batch normalization acts as a regularizer. And okay, this session is talk about efficient grid size reduction. Traditionally, convolution network use some pooling operation to decrease the grid size of the feature maps. In order to avoid a reputational bottleneck, the activation dimension of the network filters need to be expanded before applying maxima or average pooling. This means that the overall computational cost is dominated by the expensive convolution on the larger grid. Another method is switching pooling with convolution layer, and this reduces the computational cost by a quarter. However, this will create a reputational bottleneck as the overall dimensionality of the reputation drops, which resulting in less expressive networks. Instead of doing so, authors suggest another variant that reduces the computational cost even further while removing the reputational bottleneck. We can use two parallel stripe toolbox, P and C. P is a pooling layer, and C is the convolution layer. Both of them are stripe 2, the filter banks of which are concatenated as the following figure.
I'm now going to introduce the sixth part of this paper. It's a summary of the ideas that we just mentioned, like factorize the convolution layers into smaller convolutions, spatial factorization into asymmetric convolutions, expanded the filter bank output, and grid size reductions. And I would like to briefly tell you what the architecture look like. There are several conventional convolution layer in the beginning and 3 new inception module. We call inception module A and 5 inception module B and 2 inception module C. And the input size and the input side of every layer is the output side of the previous layer. So, and the reason why the input size at the beginning is 299 times 299 times 3 is because the data set we use is ILS-VRC 2012 classification benchmark. And we would like to compare our model to Google Net and VGGNet, which are winners and the second place of this challenge. And to see more clearly to this architecture, 6 convolutional layers and the input size gradually become smaller and smaller, and 3 inception module A. Inception module A is the inception module that including the convolution factorizing into smaller convolution, and 5 inception module B, asymmetric convolution included, and 2 inception module C. We expand the filter bank output at this inception module. And at that moment, you may think, are the inception module the same convolutions? Actually, they are. And the reason why the input size becomes smaller and smaller between this inception module is because we put the grid size reduction module between them. So this is the reason why the input size becomes smaller and smaller between these inception modules. And there is a visualized graph of our model that could make you remember this model easily. 3 inception module A and grid size reduction, 4 inception module B and grid size reduction, and 2 inception module C. And there is an auxiliary classifier that we mentioned to act as a regularizer in this model. And I have some comments on Inception V3, and there are 42 layers in this model that makes the computational cost 2 times 5 higher than the Google Net. But they also think that is tolerable, and the model is more efficient than VGGNet. And because it follows the principle we mentioned, the balance the width and depth of the network, so the model is relatively stable. And I want to make a quick comparison between Google Net and Inception V3. In Google Net, there are 9 basic Inception modules in this model. And in our Inception V3, there are also 9 Inception modules, but the new Inception module and the grid size reduction involved in our models.
Okay, since the purpose is to improve image recognition, they set code entropy as loss function and softmax as activation function on output. However, this method may cause overfitting. Hence, they propose the new regularization method called label smoothing. Suppose the 1/2 vector is k dimension. At first, we initialize the constant epsilon. If the element in the vector is equals to 1, we turn it into 1 minus epsilon. If the element and others turn it to epsilon divided by k minus 1. For example, suppose the 1/2 vector is 6-dimensional vector defined as here, and we set epsilon to be 0.1. Then we transfer the vector to first x 1 minus 0.1 and others are 0.5 divided by 5. And here is the result. And after we transfer the label, we use these new labels to train the model. For the experience model setting, the bench size is chosen to be 32, and the epoch is set to be 100. For the optimizer, they use momentum and RMS prop. Finally, the learning rate is set to be 0.045, and decay exponential rate is set to be 0.94 every 2 epochs. Next, another question is whether the resolution effect on the result. The common wisdom is that models implying higher resolution receptive field tend to result in significantly improved recognition performance. However, the computational cost is more higher as well. Hence, they design 3 experiments with different input size and network structure, but has almost identical computation cost. And here is the experiment result. We can see that the top one accuracy has no big difference in 3 models with almost identically computation cost.
Okay, let's back to the result and the comparison. The table on the left is the result of versions of Inception from Inception V1, Inception V2, and multiple fixes and label smoothing, and finally to the auxiliary fixing and the highest quality version of V3. And on the column is the top 5 and the top 1 and the computation operation in the unit of billions operations. You can see that the Inception V3 got huge improvement on the result, while only modest extra increase on the number of computations. The 2 tables on the right are the comparison of Inception network and its competitor. Note here there are some of the network apply multiple crop evaluations in their chain and inference stages. On the bottom right is applied with ensemble learning with multiple models trained to obtain the results. And finally, back to the conclusion. Based on the 4 design principles, the authors design a higher performance vision network and take care of both a number of computations and the inference accuracy. For the accuracy, Inception V3 had a 25% reduction on the result, better than Google Net. And it also beat p-ReLU and VGG, and furthermore have a higher computational efficiency and only 1/5 times number of parameters. And it has nearly identical result in 75 by 75 pixels low resolution classification tasks, which would be great for other purpose like selector of masking in object detection, for instance. And there are many strategies in this improvement, which could be used for other deep learning models in the future. And this is the end of our presentation. Thank you for listening. Are there anyone have questions?
So questions once.